Welcome to a read along with Dr. Pell, the book Discrete Perspectives in Mathematics. This is subsection 5.4.6. We're going to be looking for more relationships between number of derangements and be looking at polynomials or series, even multiplication. So let's take a look at this and kind of see for a minute. Notice this D3 here and this calculation here. Let's go back to what we had up here. See this 3 factorial times all that? That's kind of what I represented right here. So 3 factorial times, and I distributed 3 factorial to each part. Similarly, let's do the same thing for D2. If we were able to compute it in the same way, we'd have a 2 factorial, and we'd be having this minus that plus this in a similar manner. You could work that out and see that. If you're for D1, you'd have this. For D0, you'd have this. So this adds to D0, that to D1, that to D2, that to D3. Okay, so we have 4 different equations, but I just wrote them like this in columns. So let's take each equation. We're going to divide each equation by something, and it can be different for each column. It's okay because you still have equations. So let's see, for this column, let's divide it by 3 factorial, this one by 2 factorial, 1 factorial, 0 factorial. So we're just left with these guys right here. And this is D3 over 3 factorial, D2 over 2 factorial. D3 counts the number of derangements, size 3, number of derangements, size 2, size 1, size 0. So we end up getting, okay, so we end up getting this. And so dividing is the same thing as multiplying by the reciprocals, which is what was written right there. Okay, so this table looks like a multiplication. Mod x to the 4th of 2 polynomials. Really? Let's think about that. So I have 1 0 factorials on the top. I have all these guys are the same here, same here, same here. So what am I multiplying by? It looks like we have like a 1, 1, 1, 1, and we're multiplying that by like 1 0 factorial, 1 over negative 1 over 1 factorial, and then plus 1 over 2 factorial, and so forth. In fact, like this, like a 1, 1, 1, 1 coefficient, and then this right here. So like we're multiplying those two guys together, all right? And that's going to be, at least mod x to the 4th is going to be equal to this sum right here, where our coefficients look like d1 over a factorial, d2 over a factorial. So really, the derangements are now coefficients of a polynomial. All right. Now we're working in mod x to the 4th. So we could think, if we use the fact that this is really a truncated version of the series for e to the negative x, mod x to the 4, we could actually even write e to the negative x and just remember that we're truncating it, so mod x to the 4. So we could write that down. So this guy right here is going to be congruent to what we just have here. We just rewrote this as this, and then here's the statement of rewriting this with that. Now on both sides, what if we multiply both sides by e to the x? It goes away over here, then you have e to the x times something over here, and you're modding out by x to the 4th. Working in mod x to the 4th. Okay, so so let's take a look at what we have so far. Let's see here. Okay, this is just what we know e to the x is, all right? So this is just a statement of what e to the x is, mod x to the 4th. So this is not part of this equation right now. We're just stating it. And then we take that and we can substitute it in for e to the x over here, which is what we do here. We substitute it in, and this side we have that. And then we do multiply these polynomials together using this tabular method. And we should get that this sums to 1, this sums to 1, this sums to 1, this sums to 1. Which, just looking at this last column, looks like that plus that plus that plus that is 1. Now, if we multiplied everything by, this is interesting. So if we multiply both sides by 3 factorial, you get a 3 factorial on this side, 3 factorial on the tops everywhere. and then throwing in, okay, and then throwing in right here. So this is 3 factorial and 0 factorial, putting those together, putting those together, those together, those together. These actually look like binomial coefficients, the formulas form, which we could write this way. This is kind of working backwards, because when we were computing the number of derangements, we were like taking a factorial times coefficients with a plus or minus. Now here, we just have like binomial coefficient times derangements plus binomial coefficient time derangement, so forth, and that equals a factorial. Let's look at the difference. Okay, with what we had before when we did that. Let's go back up here, like right here. So this is equal to that times, see the difference here? We've solved for derangements. Now we're solving for a factorial. So factorial can be written this way. Well, notice this is just a partition calculation, because this counts the number of ways of choosing 0 fixed points for a permutation, one way of number of permutations, 1 fixed point, or number of ways of choosing one with 1 fixed point. So ways of, with 2 fixed points, 3 fixed points. Now with 0 fixed points, that's going to be all our derangements, right? Have 0 fixed points, and specifying that there's, right, so there's none there. Here you choose one for each fixed point that you choose. You look at the other two and you count how many derangements there are on those, and then you do it for another fixed point, how many derangements those, and so forth. What we end up getting is we end up partitioning all the permutations of size 3 into clumps. So really, each clump is, these are things that have no fixed points, things that have 1 fixed point, things that have 2 fixed points, things that have 3 fixed points. And that sums to there. So that's just another way of looking at it. Okay, so this was just a little example of polynomial multiplication and how it can be useful sometimes. And honestly, we didn't really see anything new, except we just kind of noticed that we were actually able to solve for the factorial in terms of derangements, just like we had derangements in terms of factorial. And sometimes that can be useful. This is mainly just for interest's sake here at this point. Thanks for watching.